Hello, everyone. I'm glad you were able to join my talk virtually today. My name is Adarsh Shah. I'm founder and CEO at Computest. My talk today is From Infrastructure as Code to Environment as Code, Challenges Scaling Infrastructure as Code and How to Resolve Them. This talk is based on my and my team's experience working with and helping various companies adopt infrastructure as code and the challenges that we have seen scaling infrastructure as code over the years. I will also introduce environment as code, which has helped us resolve those challenges. Also, some of what you will hear today around environment as code is new. So I would love to get your feedback, answer any questions, and discuss it further. We all know what infrastructure as code is. It helps us automate provisioning of infrastructure resources. It is one of the key DevOps practices that enables teams to deliver infrastructure rapidly and reliably. Here's a typical evolution of your IaC. You probably start with a very simple setup, a monolith IaC with a single run. If you are using Terraform, then that means a single state file. As you can see in the diagram on the left, it has networking, platform EC2, and S3 bucket, all in a single monolith IaC run. As you scale, you start breaking the IaC into separate and smaller IaC runs. As you can see in the diagram on the right, there is a separate network infrastructure as code, and then platform EC2 and platform K8s and Postgres that depend on networking. And then the K8s add-ons that depend on the platform K8s. This talk is focused on teams who have already broken down their infrastructure as code into smaller runs or looking to do that. If you have a very simple setup and can just execute it as a single ISC run, you won't have most of the challenges we talk about today. For the execution of your ISC, it probably starts with running ISC on the engineer's machine. You have a very simple setup. Probably only one member of the team is using infrastructure as code. But as you mature, you have more members of the team that want to run the ISC and want a more reliable and stable execution environment. You can create an ISC pipeline or use GitOps to execute the infrastructure as code from a shared environment. This talk is focused on teams who already use some kind of a shared execution environment, either pipelines or GitOps, or they are looking to do that. Now, we know that application teams need an entire environment, something like you see in the diagram, to deploy and operate their applications. Just getting networking or your Kubernetes cluster or RDS database on its own is not going to allow them to run their applications. They need an entire environment, whatever that might mean for you, for the team. That has the various infrastructure resources and dependencies between them. In this environment network example environment, networking needs to be provisioned first, and then platform EC2, then your K8s, and then your K8s add-ons. If you want to get an environment like this using infrastructure as code, here are your options. Option 1, create a monolith ISC. But we all know this is bad. It creates tight coupling and is not recommended unless, of course, you have a very simple use case. The state files become large and it becomes painful to maintain them with a monolith infrastructure as code. Option 2 involves hand-rolling pipelines using tools like Jenkins, Circle CI, etc. to run the IaC and managing complex dependencies in the pipeline code. When your IaC is declarative, while your IaC is declarative and idempotent, these pipelines are not. You have to write a lot of custom code to provision an entire environment. For example, again, logic for executing networking layer IaC first, and then executing the platform K8S layer, and then the K8S add-ons layer. Teardown must be supported, and any failures or errors that impact the environment must be accounted for as well. If there are failures or errors while execution, they usually get managed manually by engineers outside the pipeline. As you can tell, these options are inefficient, costly, and typically requires a dedicated team. Here are some of the other challenges scaling infrastructure as code. If you want to follow principles like immutability, which I'll explain in detail later, for your environments, or make it easier to share best practices implementation of environments across various teams, having a mechanism to easily replicate environments is critical. Since the above pipelines are not ideal, the ones that I mentioned in the previous slide, for managing entire environments, it becomes painful to replicate them. Teams spend a lot of time writing custom code to replicate environments. Visualizing and understanding environments is painful. Teams also struggle to visualize and understand environments like dev, QA, or production that they provision using infrastructure as code. Trying to find that information by going directly to the cloud provider's dashboard is even more confusing. If they want to troubleshoot an issue, share knowledge between teams, or make any changes to existing environments, they need to go through a painful and time consuming process. A lot of teams create diagrams for their environments with various infrastructure resources and how they are connected using tools like Visio or Draw.io. But these diagrams get out of date soon with real environment. Instead of helping, they actually provide incorrect information and can cause confusion. Over the period of time, due to human error or indirect changes, provision infrastructure drifts from the desired state in the code. With existing solutions, like using a pipeline to execute infrastructure as code, drift can be detected since IaC is declarative, but only when that pipeline executes the IaC next time. And it'll only find drifts within that particular IaC. Teams should know about the drift right away, and not just for individual infrastructure resources, but for the entire environment. Various component dependencies so that they can remediate any issues as soon as possible. Now that we understand the challenges scaling infrastructure as code, let's understand what environment as code is and how it helps resolve those challenges. We can start by looking at a really high level diagram of environment as code. Environment as code is just an abstraction over infrastructure as code. As you can see in this diagram, IaC, which is environment as code, versus IaC, which is infrastructure as code. This IaC is declarative and executes and manages various infrastructure as code pieces like networking, again, your Kubernetes clusters, your Postgres database, KDS add-ons, etc. Various infrastructure as code components are responsible for provisioning infrastructure resources. Um, and environment as code is responsible for executing infrastructure as code in the right order, as you can see in the animation. Here's the difference between infrastructure as code and environment as code using Lego technology. Infrastructure as code automates various Lego pieces that are your infrastructure resources, or maybe a group of them, which I call infrastructure components. On the other side, environment as code helps you automate how Lego pieces are connected to make up a Lego toy, which is your entire environment. That is what is useful to application teams to run their applications. Here's a definition, and I know it's long, but I think it's important to read through it and understand what it is. Environment as code is an abstraction or infrastructure as code that provides a declarative way of defining an entire environment. It has a control plane that manages the state of the environment, including relationships between various resources. It detects drift as well as enables reconciliation. It also supports best practices like loose coupling, idempotency, immutability, etc., for the entire environment. IaC allows teams to deliver entire environments rapidly and reliably at scale. Now let's dig deeper into provisioning flow using environment as code. So again, you write your environment as code in a declarative way. You push it to some kind of a source control. There is a control plane, as I mentioned earlier, with environment as code that watches, let's say, a repository, and it kicks off the provisioning process. It manages the environment state, which is managing dependencies and statuses of various runs. And then, since this is the first time you're provisioning, let's say, there's no drift detection, but it realizes that the environment hasn't been provisioned yet. So it'll start provisioning environment from the first layer, which again is networking. As you can see, networking has its own state. That is, your networking box there is your infrastructure as code, which has its own state managed by something like Terraform, or if you're using Pulumi. And then after networking, it'll start provisioning the next layer, which depends on networking and manages that state. And then comes Gate as add-ons. So as you can see, environment as code, again, is just an abstraction. It controls the various components, infrastructure components that are provisions using infrastructure as code, and has a control plane that is uh, the place that how it manages the environment state, detects drift, and reconciles changes. And infrastructure as code is actually responsible for provisioning actual resources in your cloud providers or wherever else you are provisioning. In case of tearing down environment, it knows that it has to reverse the logic, right? It starts destroying resources from the leaf node. Um, it's the same way how tools like Terraform or Pulumi do it, but this is an abstraction so that you don't have to create this monolith infrastructure as code. All right, now that we know what environment as code is, let's look at the various attributes of environment as code. As mentioned earlier, environment as code manages an entire environment. So it should support defining the entire environment with various infrastructure components in an easy to understand format. It also supports specifying various relationships between these components. This diagram shows an example environment as code using YAML custom format. We use this for our product, Z Lifecycle, but it doesn't have to be a YAML format. You can use any format that allows you to define these various components, how they run, and their relationships. As you can see in line 54, we have a type Terraform there. It can be any other type like Pulumi, CloudFormation, whatever your tool or language of choice is. And then it also defines the dependencies in line 55. In this case, platform EKS is dependent on networking. Environment as code promotes loosely coupled infrastructure as code components. Again, like networking, platform KDAS, Postgres, etc., as you can see in the diagram. And I have been showing that again and again to make a point. So environment as code then brings these loosely coupled components together to give an entire environment, which promotes and helps engineers to create smaller and loosely coupled infrastructure as code components. Like infrastructure as code, tools have state files to capture the state of each run. Environment as code also has a state file that captures the state of the entire environment run, including the various components and their relationships. As you can see in the diagram, it has operation and status, line number 6 and 7, at the highest level, at an environment level, to see what that status is. Again, this is similar to a Terraform state file, or if you're using other tools, their state file that manages the state. It also tracks component level operations and status from the last run. So if there are any failures, it knows which part of your environment execution or environment component failed. So when you rerun it, it kind of maintains that and manages that automatically. Also, if something changes and if there is a drift detected in one of the higher level components, then it'll also trickle down and run the lower level components and provision those child components automatically. Because if networking changes, you might have changes that might affect your child components. Idempotency and immutability are key principles for infrastructure as code. How do you apply those same principles to entire environment? Let's first understand what they mean in case you're not aware of these principles. So as you can see in this diagram on the left side, there is a non-idempotent example, and on the right side, there is an idempotent example. So for the non-idempotent example, let's say you need 3 VMs and you write your code, provision those 3 VMs. If you reapply the same script or code, it'll give you 3 VMs again in the non-idempotent use case, unless you write some custom code to actually check for existing VMs and not provision if they are already there. But you need to write that custom code. And then instead of getting 3 expected VMs, you actually got 6 in this case. On the right side, for the idempotent use case, you provision your 3 VMs the first time. And if you reapply the change, it actually knows that the 3 VMs are already there. So it doesn't apply any changes. So an idempotent infrastructure as code already takes care of checking for the state and doesn't provision things if they are already there. So you get the 3 VMs you expected, and that's good. So idempotency means no matter how many times you run your infrastructure as code and what your starting state is, you will end up with the same end state. This simplifies the provisioning of infrastructure and reduces the chances of inconsistent results. With environment as code, you can achieve idempotency for the entire environment, as it tracks state for the entire environment, knows what the last operation was, and it states, as we saw in the previous slide. Pipelines won't do that for you. If you write pipelines, you have to write all kind of custom logic to actually check for things at an environment level. It'll still do it at individual infrastructure resource level, but not at a higher level. In case of environment as code, it'll do it at a higher level. Now, configuration drift is a huge problem with infrastructure. It occurs when, over a period, there are changes made to infrastructure that are not recorded, and your various environments drift from each other in ways that are not easily reproducible. This usually happens if you have a mutable infrastructure that lives for a long time. These issues can be resolved by using immutable infrastructure. So now let's actually look at how it works using the animation here. So as you can see on the left, we're talking about mutable infrastructure. So first we provisioned, let's say 3 VMs again with version 1 of your infrastructure. You make some changes to your code and you want to provision the V2 version of your infrastructure. In case of mutable infrastructure, you would apply those changes to the same VMs. And you keep on patching the same VMs and updating them again and again. So that means these infrastructure or these VMs in this case are long lived, and there are chances of configuration drift over a period of time. On the right, though, if you provision your VMs, the V1 version, and then make any change, instead of patching existing VMs, you actually provision new virtual machines with version 2 of your infrastructure. And then you direct all your traffic to the new VMs and then get rid of the old ones. This way, you're always provisioning new infrastructure and new VMs in this case, so that you don't have that long lasting infrastructure. Immutable infrastructure means instead of changing an existing infrastructure, you replace it with new. By provisioning new infrastructure every time, you're making sure it is reproducible and doesn't allow for configuration drift over time. So why not apply this principle to the entire environment? You can do that using environment as code. You can replace entire environments by bringing brand new environments instead of changing existing ones to achieve immutability at an environment level. Uh, we will look at some examples and talk about how we'll be replicating those environments easily in the later slides. As mentioned earlier, teams usually create diagrams using tools like Visio or Draw.io and then keep it updated as they change code. You all know how that goes. The diagrams get out of date over a period of time and provide misinformation and are more harmful than useful. Since environment as code is simple, easy to understand format, you can use it to create a visual or generate a visual that helps team understand theirs as well as other teams' environments within your organization. This screenshot is actually from our product Z Lifecycle that we created this visual using the environment as code that we use, that you actually looked at an example earlier in a YAML format. Environment as code has a control panel, and it has a reconciler that observes whether the desired state in the source control and the actual state, that is your actual environment, has drifted, and then reconciles them. You might be thinking this looks like Kubernetes controllers. And yes, it is based on the same concept. In this case, though, it probably makes sense to have an approval step before bringing the actual state back to the desired state, as this might involve destroying or recreating infrastructure. And you don't want to be destroying something, especially if it has data or some kind of a persistent data without actually looking at what it's going to do. So as you can see at the bottom, during reconcile, it preferably should have an approval process where someone looks at what changes will happen and then approve them. Comparing and promoting changes across various environments become a lot easier with environment as code. Since environment as code is an easy to understand format and pushed to source control, you can compare the various environment as code files for your different environments and then promote changes. You can also use GitOps for the entire environment using environment as code. So let's look at how that GitOps flow would look if you try to apply that at an environment as code level. So on the left, as you can see, you push your environment as code, something similar to what we saw earlier. You push it to a branch, you create a pull request. Then you can probably have a webhook that does some kind of validation of your environment as code to make sure it's valid. Then someone from within your team or the team that owns that repo looks at the code. If everything looks good, they approve it. The change gets merged. When that change gets merged, the control plane for environment as code is actually observing that repository. It picks up the change and then reconciles that change into your cloud provider or wherever, whatever you're provisioning. Actually, these things can be used to provision GitHub repositories or GitHub users, collaborators, and stuff like that. Anything that your infrastructure can provision and maintain. So here are the attributes that we went over today for environment as code. First one is ability to define an entire environment rather than just individual infrastructure resources or a bunch of them as a group. I call it environment infrastructure components. They promote loosely coupled infrastructure as code. They manage state for an entire environment um, and let infrastructure as code manage states for individual infrastructure components. It supports item potency and immutability for entire environment. Uh, you can easily visualize and understand environments using environment as code. It supports drift detection and reconciliation for the entire environment. And then you can compare and promote changes between various environments so they are more controlled and you can audit them. Thanks everyone for attending my talk. Please feel free to reach out if you have any questions about infrastructure as code, environment as code, or even our product Z Lifecycle that makes environment management easy across various cloud providers as well as on premises. And it actually uses this environment as code concept. As I mentioned at the start, I would love to get your feedback on environment as code and discuss it further. Thank you again.